Today, we're going to look at improper integrals. And today, what we're going to look at is what if you integrate up against like an infinite discontinuity or a vertical asymptote. So we're going to take a look at that. So 1 over the square root of x has a vertical asymptote at x equals 0. Okay. If we were trying to find the integral or the area between the curve and the x-axis, and we went from a to 1, that would be a definite area right there that we could find. We've done that a lot of times. So this one for this area right here would be the integral from a to 1 of 1 over the square root of x dx. Well, how do we go about finding the area when up here, I mean, it's getting this, the curve is getting closer and closer to the y-axis, right? So how can we do that? Well, what we have to do is, again, we have to do this with a limit. So what we wind up doing is if we want to take the integral from, let's say, 0 to 1, and this has an infinite discontinuity at x equals 0 because it makes the denominator 0. And we wanted to integrate from 0 to 1, the square root of x dx. What we could do is take the limit as a, because this is going to be our lower limit a, where the infinite discontinuity occurs. And we're going to make a approach 0, but we have to approach 0 from the right side of it, from the correct side of it. And that would in turn be the right side. So we'd go, we take an a as a approaches 0 from the right of the integral from a to 1 of 1 over the square root of x dx. So we wind up with this integral with an a involved in it. And then we just take a look at, okay, what's the limit as a approaches 0 from the right? And we're going to need to do this every time we're trying to integrate up against an infinite discontinuity. All right. So for this first one, okay, if fx is a continuous function on the half open interval a to b, then the integral from a to b f of x dx. So it's going to be where a, it's going to be this lower limit right here, where we're going to have a vertical asymptote. Okay, so we have an infinite discontinuity. At x equals a. So if we have this happening, that's the lower limit where the vertical asymptote is happening, then we're going to have to pick this to be some letter, okay? And we're going to have to approach, we're going to have to let this lower limit approach this a from the right-hand side, because that's going to be where our infinite discontinuity. Well, what if it happens on the left? Like, what if it's happening at b? Okay, then we'd make this be our c, okay, and we take the limit as x approaches b, but not from the right, from the left, because it's the upper limit that's going to be where the vertical asymptote or infinite discontinuity. So this one would have an infinite discontinuity at x equals b. So what you'd want to do is, okay, am I approaching that infinite discontinuity from the right or from the left? Well, sometimes we want to integrate all the way across and go across a vertical asymptote. And that's what this is. Okay, so if we have from a to b and there's some infinite discontinuity in between a and b, then we're going to have to break this up into two integrals. All right. And so what we're going to have to do is we're going to have to break it up at the integral from a to c, and then c to b, and then c. Okay, so whatever the c is, that's going to be where the infinite discontinuity is. And then we're gonna have to do we're gonna have to rewrite this as the limit as x approaches c. Since this is the upper limit for this one, we'd have to approach c from the left. And here c is the lower limit, all right? And then we have to approach the limit as x approaches c from the right-hand side, because this area, okay, this integral would be to the right of c. So again, this one we'd have to do this and then break it up into two of these, is what I'm basically saying. And this would happen if we have an infinite discontinuity in between the lower and upper limit that we're trying to integrate. So this would have an infinite discontinuity at x equals c. And then this is important, okay? Because like earlier, like some of them, when we did improper integrals the first day, some of them, we got a value out of it, and some of them went to infinity or negative infinity. Well, when they go to infinity or negative infinity, we say that the integral diverges. If you get a value out of it, then we say it converges. So for this to exist, both of these, and this is what this important note is, if we integrate from a to b, fx dx converges, and it's only if this integral from a to c and this integral from c to b converge. Otherwise, if either one of those doesn't converge, doesn't give us a number value, then the original integral won't converge either. Okay. And then there's going to be some rules here that I'm going to show you. Like, okay, we know when we see this, the function's going to either diverge or converge, and it has to do with powers. Okay. And we're going to talk about that later on, more about that when we start doing some tests of some different things that you'll see. Oh, we did this earlier. Yeah, we did. Okay. So let me talk about that. This I can't really explain yet why. Okay. So we just got to understand this is true. Okay. If we try to integrate from 0 to 1 of 1 over x to some power dx, okay, if this power p is 1, okay, and we would have this 0, this lower limit is where the infinite discontinuity occurs at. If that's a 1, then we know this integral diverges. We also know it diverges if the power of x is greater than 1. If the power of x is between 0 and 1, so like x to the 0.5, x to the 1/4, any of those, and this is where the infinite discontinuity occurs, then what happens is we say it converges. It's actually going to come to a value, okay? And we're going to need this to know whether these are going to converge or diverge. And we can use this to tell us really quick on these specific types of functions. So for this integral, if we want to integrate from 0 to 3, and basically this is 1 over x minus 1 raised to the 2/3 power dx, we got to realize, okay, in between 0 and 1, we have an infinite discontinuity at x equals 1, okay? So the integrand, that's the thing we're integrating, has an infinite discontinuity at x equals 1. And, so I shouldn't have put a period there, and is continuous on starting at 0. It's continuous at 0. Okay, so starting at 0 to 1, not including 1, union, and then 1, 2, 3, including 3. It is continuous at 3, because if we put 3 in here, we can get a value. Okay, so what that means is we've got to break this up into two integrals. And then at x equals 1, we're going to have that infinite discontinuity. So this integral from 0 to 3 dx of x minus 1 to the 2/3 power I already wrote dx. Let me get my whiteout. Okay, we know we can break this up into the integral from 0 to 1 of 1 over x minus 1 to the 2/3 power, dx. And then we need to add the integral from 1 to 3 of the same integrand, 1 over x minus 1 to the 2/3 power dx. And then because 1 is the upper limit, right? We're going to integrate from 0 to 1. So that's the right side. So we have to approach 1 from the left. So this is equal to the limit, as I'm going to call this upper limit b, as b approaches 1. And since we're integrating from 0 to 1, we have to approach this 1 from the left side of it. So from the left of the integral from 0 to b of 1 over x minus 1 to the 2/3 power, and then plus, so this time it's the lower limit where the infinite discontinuity occurs. So we're going to add the limit as, and I'm going to call this one a. So I'm always going to call the lower limits a and the upper limits b. Okay, so this is going to be the limit as a approaches 1. But for this one, because we're integrating from 1 to 3, we have to approach 1 from the right-hand side because this area would be in between 1 and 3. So we got to get to 1 from the right-hand side. So limit as a approaches 1 from the right of the integral a to 3 of 1 over x minus 1 to the 2/3 power dx. Okay, so what I like to do on these problems is, because they can get really messy because we have two integrals we need to do, we have a limit to do and all that. What I like to do is come down lower in my page, and I like to actually do these integrals. Now, the antiderivative of both these is going to be the same. Okay, so when we integrate, we can do it. All right. So what would the integral from 0 to b? So I'm going to come down here and I'm going to slide my paper up just a little bit more. And so I'm going to take the integral from 0 to b of 1 over x minus 1 to the 2/3 power dx. Now I'm going to do a u substitution. So I'm going to let u equal x minus 1, and then du would simply be dx. So this is equivalent to the integral from 0 to b of u to the negative 2/3 and then du. Because this would be my u and it'd be u to the 2/3, right? Okay. A lot of times we'll switch the integrals here, but I'm going to switch this back to x's just to help us. Okay. So I'm not going to leave this. I'm not going to leave this with u's. Okay. So I'm not going to integrate. I'm going to change this u back to my x. Right. So when I integrate this, I'd add 1 to the power, right? So that'd be adding 3/3 to this. So this would be u to the 1/3 and divide by 1/3, but that's the same as multiplying by 3 over 1. So this becomes 3 u to the 1/3 power, and we're going to evaluate this from 0 to b, but these are x values, so that means I have to switch this u back to x. So this, and my u is x minus 1. So this becomes 3 times x minus 1 to the 1/3 power, and I want to evaluate this from 0 to b. So that's going to be 3 times b minus 1 to the 1/3 power minus 3 times, and if I put 0 in here, that'd be 0 minus 1, so that'd be negative 1 to the 1/3 power. And so that's what, when I evaluate this integral, that's what this is. And then I'm going to have to take this limit as b approaches 1 from the left. So what is the integral from a to 3 of 1 over x minus 1 to the 2/3 power dx? Well, we already know that the antiderivative is this, so we could just go, okay, that's going to equal 3 times x minus 1 to the 1/3 power evaluated from a to 3. And so this one would be 3 times, and 3 minus 1 would be 2 to the 1/3 power, and then minus 3 times, and then this would be a minus 1 to the 1/3 power. So back up here, we can rewrite this as equals, and then I'm going to replace this with my integral. So this is the limit as b approaches 1 from the left of, I'm going to use a bracket around this. It'd be this 3 times b minus 1 to the 1/3, and then minus 3 times negative 1 to the 1/3 power, and then plus, and then I'm going to add the limit as a approaches 1 from the right of, and then it'd be this one, so 3 times 2 to the 1/3, then minus 3 times a minus 1 to the 1/3 power. And now it's a matter of evaluating the limit. So when you do a one-sided limit, it's always good. Can you put in, just plug in this case, 1. Okay. So if you plug in 1, because really this is getting closer and closer to 1, right? So 1 minus 1 would be 0. So this would be 0 to the 1/3, which would be still 0 times 3. That'd be 0. So this is going to be 0. This one is not going to change. Okay. So negative 1 because there's no b here. So negative 1 to the 1/3 is negative 1 times -3 becomes +3. And then plus, and then for this one, 2 to the 1/3. Well, that's the cube root of 2 times 3. So that'd be 3 cube root of 2. And if we let a go to 1 from the right, this would be 1. We can do a direct substitution. 1 minus 1, which would be 0. And 0 to the 1/3 is still 0. Times that'd be 0, right? So it's going to be -0. So what we wind up with an answer for this is it's going to wind up being 3 plus 3 cube root of 2. And that's the exact answer to this integral. And we integrate it all the way across an infinite discontinuity, right? So that's what's going to allow us to do this. We have to change them to these limits. Now, sometimes we can, and sometimes we can't. It just depends on what the function is. And it has a lot to do with these powers. Now, so on the bottom page of the bottom of the first page, remember I talked about the powers of x. This is really a power of x. It's just been a translation to the right one. But the power here is 2/3. Well, that's between 0 and 1. And since this is between 0 and 1, that's why this converge. Okay. So if this power right here was 1, we wouldn't have gotten a value here. And if it was bigger than 1, we would not have gotten a value here. Okay. So then we want to evaluate this one and the integral from 0 to 1 and taking a look at this. Okay, if 1 right here, if we put 1 in for x, right, we're going to get 1 squared. So that's going to make this denominator become 0 because it's going to be 1 minus 1, and that'd be 0, and square root of 0, 0. So this is going to cause us to have an infinite discontinuity at x equals 1. So here we have an infinite discontinuity at x equals 1. But the integrand is continuous on, so it's not, it is continuous at 0, it's not continuous at 1. So this would be, it'd be continuous on 0, including 0 to 1, but not including 1. All right, so that means we got to write this as a limit. Okay, so the integral from 0 to 1 of 1 over the square root of 1 minus x squared dx becomes, and since the infinite discontinuity is 1, I'm going to call this one my b, so I'm going to let b. So the limit as b approaches 1, but from what side of 1? Since we're integrating from 0 to 1, we want to approach 1 from the left side of 1. And then this is going to be the integral from 0 to b of 1 over the square root of 1 minus x squared dx. So what we have to do on this is recognize that this is the derivative of something, right? We can recognize the antiderivative, and this is the derivative of sine inverse of x. So if we integrate this, then that's going to give you sine inverse of x, right? So this winds up being the limit as b approaches 1 from the left of sine inverse or arc sine inverse of x evaluated from 0 to b. So that would simply be the limit as b approaches 1 from the left of, and then it would be sine inverse of b, and then minus sine inverse of 0. Okay, now you got to recall that for trig functions, we put an angle in and we get a ratio out. So the inverse trig functions, these are ratios and we get the angle out, right? So this is not an angle right here. You got to remember that. This is a ratio of y to r. And this is also a ratio. Okay, so what happens when that ratio gets closer and closer to 1? And remember, the ratio for sine is sine of theta is my y over my r, right? The y coordinate over the radius. Well, when would this be 0? When would y be 0? Well, that would be for the angle 0. So this one's going to be 0. And this one, we could just put 1 in here. So the limit as, I didn't mean to write that. if we do this, this becomes sine inverse of 1 minus sine inverse of 0. So this one, the only way for this ratio to be 0 is when the angle is 0. So that happens right here. So the angle, this one is angle 0. When do we get y and r to be the same value, like both be positive? Okay, so it's going to happen for sine inverse right here, right at 90 degrees or pi over 2. So this winds up being pi over 2 minus 0, or that's simply pi over 2. Now, another thing to recall is that sine inverse, you can only get values rotating up into the first quadrant with a positive angle or down into the fourth quadrant with a negative angle. So these angles that we get have to be somewhere in between negative pi over 2 and positive pi over 2. All right. All right. And that's how you evaluate that one. So this one is pi over 2, the answer to this. And so it converges. Anytime we get a value, it converges. Okay. So this is going to be called the comparison test. And this is just a test to just see if a function converges or not. Okay. So we let f and g be continuous on this half open interval from a to infinity. And this is saying that, okay, we have a function that's always bigger than another function for all x greater than some value of a. So from a on, this one, f of x, is smaller than g of x. Then if this one is going to converge, so this one in the middle will converge if the outside one converges. So if this one's converging, it's going to force this one to squeeze down and also converge. And that's what this is all about. If the outside one converges, then this inside one must also converge, okay? Because it's squeezing down. Like, for instance, this one right here, this is e to the negative x, and this is e to the negative x squared. Well, from 1 on, e to the negative x is bigger, right? And I'm going to tell you in a minute, this one converges. Well, if this one converges, this one must also converge because this one is squeezing down and it's squeezing this one down. So that's how we know if something's converging or not. If we can come up with a function that's bigger that converges, then the one that's smaller must also converge. And kind of vice versa, all right? If we know that this outside one diverges. So this one's going to diverge. It's not going to have a value if we know this one diverges. And that's what this says. Okay. So if we can show this inside one, this one that's smaller diverges, well, the fact that if this one diverges, this one's going to be larger than it. So this one's going to also have to diverge. And that's what I mean by this. Okay. So this is called the comparison test. There's another comparison test later on that we're going to look at for series that we're going to talk about, and you'll start to understand this a little bit better when we talk about it. Then it's kind of like the squeeze theorem, okay, or the sandwich theorem. All right. So for this one, okay, we have, let's say we want to integrate from 1 to infinity. Okay, e to the negative x. This is kind of a little example to explain this. Okay, e to the negative x squared dx. And we also have the integral from 1 to infinity of e to the negative x dx. Okay, and there's ways to do this, but we can tell that from this graph that this one is going to be smaller than this one. Okay, so e to the negative x squared is going to be less than or equal to e to the negative x for x greater than or equal to 1. Okay, so this one converges. So I'm just kind of giving you an example of how you would use this. Okay, so this integral from 1 to infinity of e to the negative x dx, it converges. Okay, and so since this one is bigger for all x greater than or equal to 1, right, and that's our lower limit, we know that this one's larger and it's converging, okay, because this one is lower than it. If this one's converging, then this one has to converge. So we can make the conclusion, therefore, we can make this conclusion using this comparison test that the integral from 1 to infinity of e to the negative x squared dx converges. It doesn't tell us what it converges to. That's not what this tells us. It just says it converges. In other words, we could get a value out of it. All right. Okay, so let's do another one that actually shows this in action. Okay. All right. So we want to integrate from 1 to infinity dx over x cubed plus 1, or 1 over x cubed plus 1. And we want to show that using the comparison test that this either converges or diverges. Okay. So what's the hardest part is trying to figure out, okay, what do I compare it to, right? So we're going to let, this is our integrand. Okay. So we're going to let f of x equal 1 over x cubed plus 1. Okay. What we're going to do is we're going to let g of x equal 1 over x cubed. So let me write this down and I'll explain. Okay. This one has a bigger denominator. So everything else is the same, except for this one's a little bit bigger. It's 1 bigger than this, right? So that makes this overall function always going to be smaller than this one from 1 on. Okay. So because I wrote this as 1 over x cubed, I took the one, basically what I did is I compared this to 1 over x cubed. I took the 1 off, right? And I know that this one's going to be, this overall fraction is going to be smaller than this one. So we know 0 is less than or equal to 1 over x cubed plus 1, which is less than or equal to 1 over x cubed. That will always be true because this denominator is just slightly bigger than this one, okay, for every x. Okay, so what I want to do is I want to show that this one converges. If I can do an integral and show that we get a value out of this, then we would know that this one converges. And because this one's always going to be smaller than this one's also going to converge. And that's basically the comparison test. Okay. So we want to do the same integrand. So we're going to integrate from 1 to infinity of 1 over x cubed dx. And then this, we're going to have to change this to, this is the day 1 of improper integrals. Okay. So this is going to be the limit as b goes to infinity of the integral from 1 to b of x to the negative 3 dx. So this is the limit as b approaches infinity. This would be x to the negative 2 divided by negative 2. And then we want to evaluate that from 1 to b. So this, we still have this limit, the limit as b approaches infinity. And this becomes x to the, or actually what I want to do is I want to rewrite this. I want to rewrite this as negative 1 over 2x squared. And then I'm going to want to evaluate it. Okay, so this is equal to, again, the limit. And I forgot to put the limits of evaluation. So if we want to integrate this from 1 to b, or evaluate it from 1 to b, I should say. So b approaches infinity. And this would be, putting b in, it'd be negative 1 over 2b squared. And then plus, because we're going to subtract, but this is negative, so that's going to make the plus or adding. And this would be 1 over 2. Okay, so what happens when b goes to infinity? Well, that's because I'm squaring it, right, and multiplying by 2. This is going to become really, really big. So this fraction is going to get closer and closer to 0. So this becomes 0 plus 1/2, or 1/2. Okay, so when we integrate this one that's bigger than this one, right, it converges because we're getting a value out of it. And since this one is bigger, right, then this one must, and it converges, this one also must converge. So we would say the write-up on this is like this. So since the integral from 1 to infinity of 1 over x cubed dx converges, and that's the bigger one, right? If the bigger one converges, the smaller one converges, okay? And if the smaller one diverges, then the bigger one must also diverge, right? So since this, then we know that the integral from 1 to infinity of 1 over x cubed plus 1 dx must converge by the comparison test. And that's how you show it. You gotta identify your two functions. You gotta identify that, which one's bigger than the other. And then show that, either you're gonna have to show that show that this one converges, or you need to show that this one diverges. Okay. Right. That's it, guys. All right.